All right, we'll move on to segment 3 of this unit, and here is where we begin getting into the mathematical meat of the subject. We'll start though without getting into anything terribly new, but by reviewing vectors. Okay, so in this unit we are going to review vectors. Right? I won't get into a very simple, basic, elementary sort of definition of vectors. We all know that they are directed segments. Why do we need vectors? Okay, something for you to think about. Why do you think we may need vectors in continuum mechanics? The answer is going to be quite straightforward, of course. The fact of the matter is we've already talked about forces. Pretty soon we're going to talk about velocities. We talked about momentum already. These are all vectors. Okay? So the reason to review vectors is because vectors essentially make up the language of continuum mechanics. Or they are an important part of the language of continuum mechanics. Okay, examples include the force or forces, momentum, velocity, right? And of course, there are many others. All right, so this is why we're going to review vectors. We'll start in a fairly simple fashion before we get more intense about it. We'll start by looking at two basic properties of vectors, and well, first we must lay down some basic mathematical notation. So we are going to denote vectors, okay, for now. We're going to denote vectors by the usual English or Latin alphabet. So we're going to denote vectors by U, V, W, and so on, right? We'll use as many of these symbols as we need. What we're also going to do is talk a little bit about the collection of vectors. In particular, we are going to say that U, V, W, and so on belong to what we will call a space, okay? And we are going to denote that space by E, all right? So they belong to a space, E, which is, we really want to think about the space E as just being the collection of vectors, U, V, W, and anything else. Now, we're talking about vectors in three-dimensional space, right? So we have here three-dimensional space, which we remember is so because of our three axes. That is a vector, right? So that may represent the velocity of a particle moving in this direction. This arrow here may represent maybe a force acting on this body, right? And so on. However, we just observed that these vectors are objects that live in three-dimensional space. So they belong to the space E, which itself is a subset of R3. Okay, because these are vectors in three-dimensional space. In addition, we will also need to use some notation for scalars, right? So we denote vectors by U, V, W, and scalars. For scalars, for now, we will use the Greek letters, right? So we will use alpha, beta, gamma, and so on. If the vectors belong to a space E, which is a subset of R3, what do our scalars belong to? What kind of space do our scalars belong to? Something for you to think about for a few seconds. Our scalars belong simply to the space R. They're just real numbers, right? So you can think about them as living in one-dimensional space denoted by real numbers. Okay, so that's the notation we have. Okay, let's move on. We're going to look at two basic properties of vectors. The first property the first property is what we will call multiplication by a scalar, right? So how do we do this? If we have a vector u belonging to our space E and a scalar alpha belonging to the space of real numbers, then we can define another vector v also belonging to E, because it's just another vector, such that v equals alpha times u. Okay? So what this simply means is that the scalar multiplication of a vector gives us another vector, right? Basic enough and straightforward enough. The next property we will look at is vector addition. And the way this works is that if u and v, let's say uv and w belong to E, okay, then we have this notion of the addition of vectors. So we can say that u plus v gives us another vector w, all right? And we all know how this works. In high school, I guess, we all learned that if that is our vector u, we bring in another vector v, right? We were all taught this geometric construction, and here I'm going to use the parallelogram rule for addition of vectors, right? Let's see if I can draw this well, right? We do that, okay? We complete the parallelogram defined by u and v, and we get the vector w. Okay? And this is the parallelogram construction. Okay? That's what allows us geometrically to define what u plus v is. And in this case, it's w shown as drawn. Of course, there's another rule, right? The triangle rule, and they're essentially equivalent. Okay? It turns out that this property of vector addition has, and actually even the property of scalar multiplication of a vector have certain additional features. We have, in both cases, we have the identity element. Okay? For scalar multiplication of a vector, multiplication. Okay, so the way to read that is the identity element, perhaps, of scalar multiplication, right? What this is the following. We know that if we multiply 1 into a vector u it gives us back u, right? So that's the identity element of scalar multiplication. Okay? Likewise, we have the identity element of vector addition. The way we write that is u plus the 0 vector equals u. And then we have the null element of scalar multiplication right, which is the 0 scalar times a vector u equals the 0 vector, and the null element of vector addition. Okay? And the way that works is u plus the minus u vector equals the 0 vector. Okay? So these are basic properties of vectors. What we are going to do now is recall fairly quickly two other basic multiplication operators on vectors. Okay? And we're going to start with one that's very familiar, what is called the dot product of vectors. Okay? It's also sometimes called the scalar product, or even the inner product. Okay? Scalar or inner product also. This is something that you're very familiar with, and the way this works is the following. We say that if u and v belong to E, and if alpha belongs to R, then the dot product of u and v is written as u dot v equals alpha. Okay? So we have a product that's defined with two vectors, u and v, giving us a scalar alpha. Mathematical notation for this is often written as E cross E mapping to R. This simply means that we take one vector from E, from the space E, take another vector from the space E, do something with them, and we end up with a scalar R. Another way in which this dot product is sometimes written is the following. You sometimes use these angle brackets and write u comma v equals alpha. In this form, this sort of representation of the dot product is often used when you're thinking of it as an inner product. Okay? This is often used for inner product. Okay? Let's just recall some elementary properties of the dot product. Let's see. All right. We know that properties, right? We know that u dotted with v equals 0 if u equals 0 or v equals 0 or if u is perpendicular to v. Okay? We also know that mathematically the way u dot v is written is the following. U dot v is the magnitude of the u vector times the magnitude of the v vector times the cosine of the angle between them, right? So if we have u, if that's our vector u, this is our vector v, and that angle between them is theta, right? Then u dot v is u times v times cosine theta, all right? Where it really doesn't matter which direction theta is measured in, okay? And that's a property of the cosine function. What this also means is that because of this representation for u dot v, we also know that u dot v equals v dot u, okay? Do you recall what this property is called? This property is called commutativity. Commutative. Okay? That means that the dot product or the scalar product is commutative. Okay? The last thing I want to say about the dot product is that suppose we take what is called a unit vector. Okay? So if E is a unit vector, okay, what this means is that the magnitude of E is equal to 1. Then u dot E, right, which is equal to u, magnitude of u times magnitude of E times cosine theta, is equal to the magnitude of u times cosine theta, because we know that E has a magnitude of 1. All right? So when this happens, we know that we denote u dot E as being essentially u resolved along the vector E, okay, or the component of u along E. That's u and this is E, and the angle between them is theta. All right? Then u dot E is often thought of as this, right? So we say this is u dot E. Okay? And I will write this here as saying u dot E is the magnitude of u along E. Okay, we're going to stop here. Okay, to complete this segment, we are going to go on and look at the other sort of multiplication operation that you're familiar with on vectors, which is the vector product or the cross product, right? So we're going to look at cross product, right, of vectors, also called the vector product. The way we do this is, again, we take a collection of vectors. We take u, v, and w, all belonging to our space of vectors E. Okay? And then the cross product is denoted as u cross v equals w. Note here that unlike the dot product, which took two vectors and gave us a scalar, we have here two vectors giving us the vector. Of course, we all know about this, right? We're very familiar with this particular operation. Using the sort of mathematical notation that we employed to talk about how the dot product maps vectors, two vectors, both from the space of vectors into the reals, we have here the following notation. We take u and v, both of which belong to the vector space E, and we are mapping it onto the vector space again E. All right? So this thing is often read as E cross E mapping into E. Note that the fact that we're using a cross here to talk about E cross E should not be confused with the actual cross product. This is just mathematical notation. Okay? So the cross that we use here in E cross E does not refer to the cross product or the vector product. The cross that we use in U cross V does indeed refer to the cross product. Okay? In much the same fashion, if we go back to this slide and look at how we wrote the mapping for the case of the dot product, right? We wrote it as E cross E mapping to R. Clearly, the cross here used on the space E does not refer to the cross product. It's just a way of saying that we're taking two copies of vectors, both from this same vector space E, and doing something with them. All right, so some basic properties of the cross product. We know that U cross V equals 0 if U equals 0, if U is the 0 vector, or V is the 0 vector, or if U is parallel to V. Okay? Continuing along the same line as we did for the dot product, let's consider what happens with this, right? So if we take U cross V, we know that it is equal to the negative of V cross U. Okay? So in particular, U cross V is not equal to V cross U. Okay? It's not commutative. On the other hand, it is V cross U except that the sign is flipped. So this is sometimes called anti-commutative. Okay, this particular property. As the very last thing, just as we gave a geometric interpretation for the dot product, right? We talked about how the dot product could be viewed as taking the magnitude of each vector and multiplying those magnitudes, the product of those magnitudes by the cosine of the angle between them. In much the same way, we can write out U cross V as U cross V equals magnitude of U times magnitude of V times the sine of the angle between them times the following vector, a vector E, okay, where E is a unit vector, okay, its magnitude is 1, and E is perpendicular to U and V. All right? So let's see how this works. If we have U and V, right, that is the angle between them. In this case, I'm taking care to indicate the direction of the angle. The angle goes from U to V, all right? And this direction of the angle is often denoted by what is called the right-hand rule. So, as an example here, if we take this vector to be U and that vector to be V, then when we talk about U cross V, we're talking about going from U to V with the right-hand rule, right? So we go this way, and then the thumb points in the direction of this cross product, right? So the thumb points in the direction of this third vector. So U cross V is in the direction of this vector, right? So the unit vector along this direction would be E, as I've just denoted here. Okay? So in this case, we would have u cross v. We're going in this direction from u to v, and therefore the vector E would be directed perpendicular to both u and v. That would be the vector E. Okay? U cross v in the direction of E. Now, you may recall that this product, the cross product, also has another sort of aspect of its geometric interpretation. Okay? In particular, what we know is that u cross v, okay, the magnitude of u cross v is the area of the parallelogram defined by u and v. So going back to this picture that I drew here, if we attempt to complete this parallelogram, all right, if I complete this parallelogram and I do it neatly, then u cross v is simply, the magnitude of u cross v as I've written it here, is simply the area of this parallelogram, right? Alternately, sometimes if we don't worry with the magnitude but just look at u cross v, it is often referred to as the area vector of the parallelogram, right? Okay? So that does it for our cross product, and that is also a good place to end this segment.